Hello, good morning, happy Monday or Tuesday, whenever you're watching this. Closer here. So this is my third take. Hopefully I can get this down this time without being interrupted a billion times. So just a reminder to please check your announcements towards the beginning of the week or whenever you see an announcement. We did finish up our Unit 2 test. I will be putting a slideshow together with the most commonly missed questions and explanations for those. And don't forget that you can retake one test per semester. So if you want to retake this test or the last one or the next one, please contact me and we can set up a time for that. I would recommend if you completely failed it and you have no idea really why, that you get a hold of me. We can do a Zoom and kind of go over some stuff, or I could explain some things through email if that's better for you. But I will be opening up the questions with the answers in the next couple of days once everybody is finished that test, so that you can view that and see what you got wrong. So we're going to start in Unit 3. Unit 3 is focused on periodic trends. We'll talk about some different trends, and then the bonding. That's kind of what this is talking about, like what we're going to be going over. Your success indicators. This is how you know if you're successful today, if you can do these things. So maybe pause that, read through those if you would like. So we're going to start out with just some history of the periodic table, and there is a large amount of content to get through today, so I'm going to try to do it quickly. So Dmitry Mendeleev is known as the father of the periodic table. He first published his first periodic table in 1869, so he was working on this in like the 1860s. Not a ton of technology happening back then. At this time, they only knew about 60 atoms or 60 different elements. And again, they didn't know a lot about them. They knew what their atomic masses were, and so he started to organize them, and by some of their characteristics, which all he really had was atomic mass. And this picture here is pretty neat, I think. So this is a scan of his original work, and you can see where he started organizing things, and he crossed things out and started over, truly kind of showing like the scientific method process there of trying and reworking and going again. So it's neat to see that was happening, back in the 1800s as well. So he started organizing these atoms based on their atomic mass. And if you look at your own periodic table, you can see that the atomic mass increases as you go. And he started organizing that way. So out of the 60 that they had, now there's 120-ish, 118 known elements now. He realized that there were some spaces in there, and so he left those areas blank. He realized that there would be kind of a gap between like fluorine and sodium, for instance. He realized that probably something else would fit in here eventually. He didn't know what, but he thought something would probably fit there. So he left room for additions to be put in later on. But what his biggest discovery was that once he organized these, they kind of came together in different groups of certain characteristics. So he realized that this whole group 1 kind of shared some similar characteristics, and group 2 shared some characteristics. And that was really pretty important. So as science and time went on, that's kind of what scientists started referencing. And then in 1911, Henry Moseley was working with Ernest Rutherford on some of his research. So we know Rutherford from his gold foil experiment, and he was figuring out that, you had a really dense nucleus and the electrons were kind of scattered, and we had protons and neutrons in the nucleus. We knew this at this time. So by now we knew about protons. We knew that the protons identified the elements probably better than the mass would, because we know that now that the masses could be in different isotopes and they could be slightly different. So when Moseley was working with Rutherford, he started thinking maybe the atomic number would be a better way to organize these. So he went back in and tried to look at Mendeleev's work and match things up by their atomic number. And he realized that he, again, came to the same discovery, that yes, like these do kind of come together in different groupings if we organize them like this. So at this point in time, he determined that there was going to be something called the periodic law, and that was going to state that the physical and chemical properties of elements are periodic functions of their atomic numbers. So that you were getting these certain groupings every so often in an organized pattern based on their atomic numbers. And that's what we're going to talk about today is all of those families. After this is over, if you want to pause this, I would recommend just like kind of looking at this picture. It's so cool that this is back in the time frame that they were actually doing this research, and these are the labs they were working in. So it's really neat to kind of just like really maybe zoom in and look at these and kind of see what they were working with. So this is going to be the second section of the notes today. So again, if you want to pause this and check out your success indicators, basically just talking about, what this is about. So we're talking about the modern periodic table, the one we know and love today, all the families. So we're going to start with the alkali metals. So that's going to be group one. All of these are alkali metals. They all have one valence electron, which we know already. And these are all alkali metals except for hydrogen. So hydrogen is not a metal, and it's over here because of its atomic number, but it does not follow these rules. So when we have bonding, let me get a pen here. Okay, so if I have, I don't have a lot of room here. I'll just write it in here. So if I have, my atoms and they have all of these dots on them, we know our Bohr models, right? So if this one has like 2 here and 1 on the outside, we know that this atom is going to be most stable with a full valence shell. Okay, so this is kind of what we're focusing on for this unit. So with a full valence shell, they're going to be stable. They're not going to react anymore. And atoms want to be stable. They're going to lose or gain electrons with other atoms around them in order to become stable. So if we're looking at this and we have 3 electrons on it, so this would be, lithium would be here. So lithium, so we do have 2 on this inner ring and 1 on the outer ring. It could have 7 more electrons fill in this ring, or it could lose this electron and become stable by this inner ring. So that's what it's going to do. It's way easier to lose an electron than to gain 7. So this one would lose that outer electron. It would become stable again, looking here. And that's kind of what this is looking at here. So all these alkali metals are always ready to give up their outer shell electron to become stable. So all of these have one valence shell electron. They're ready to give it up. It's easy to bond that with something else. So that makes them super reactive. Let me erase all this. So these alkali metals are very, very highly reactive, especially on water. That's called a Coulomb explosion, and we'll talk about that a little bit later in reactions. But some of these metals are even so reactive that they'll react with just the humidity in the air. So they're stored in oils and things so that the air can't reach them. So other physical properties we know about metals in general is that they're shiny, they're usually lightweight, they're malleable, which means you can cut them, shape them, all that good stuff. So this video, I'm going to kind of pause and go through different pieces of it, but let me turn this up a little. So this is showing 3 different alkali metals. The first one, let me see here. I think he has lithium, sodium, and potassium, and they increase in reactivity as you get further down on the periodic table. So if you have your periodic table handy, it's kind of a nice reference for this as he goes through. So he's going to start at the beginning here.
Here I'm working with some lithium metal, very difficult to cut.
Cutting them in half, showing you
sodium here,
what they look like.
You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick and see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially.
Okay, so he goes through, he cuts the metals. And again, this is all on the slides that shows. So if you want to stop and watch the whole thing, feel free. I'm just, for the sake of time, we're going to kind of skip through some of these a little bit. So he now is going to drop these in water. And if you ever find some of this, and it always happens. It doesn't happen very often, but like every couple of years, I always have a student that's like, "Oh yeah, my grandpa has a container of this in his garage." Be very careful. Like, don't play with it. It's something that is safe to mess with. Because some of these, like I said, are so reactive that once you take them out of the oil that they're stored in, they can react just with the air. They can explode just by reacting with the water in the air. So we're going to show this. He's going to put some lithium in water, and then sodium, and then potassium to show you kind of the difference in reactivity. So towards the top of the periodic table, the top left corner, they're going to be less reactive, and as you work your way down, they should be more reactive.
Gas.
And also, before he moves on, he did put some indicator in the water, so it's going to turn pink, but that has nothing to do with the reaction. Like if you just put it in water, it would not turn pink.
And lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And the last one, I'm going to go ahead and put my 2 pieces of potassium in. So this is less potassium than the other 2 in terms of amount. You'll find that the reactivity is a little bit greater.
Okay, so you saw just how reactive potassium is with water. And if you look on your periodic table and you keep on going down that column, you still have 3 more elements, and they get increasingly more reactive as you go down. So more and more dangerous as you move away. So this video, please go back and watch this. This is kind of cool. It just shows the different reactions of different alkalis with water in larger amounts. So they like throw it in a bathtub full of water. That's a really neat video. It's kind of long, so come back to it when you have a little more time. So here on the second group, we have the alkaline earth metals. So these are also very reactive, not as reactive as the alkali metals, but still very reactive. They have 2 valence electrons. So if we were drawing our Lewis dot diagram, you might have, hold on, let me get in here. It's hard to do on a computer. Okay, so if we had like magnesium, right? It's going to have 2 dots. We know that. So 2 dots, you have 6 more spaces to fill in. So magnesium and all of these in group 2 are going to very readily give up those outer electrons. So we know that once they give those up, the next ring down would be full. So then it would be stable. So in order to become stable, everything in this group 2 wants to get rid of its valence electrons. So they're going to easily bond as well. So they're also going to have a pH greater than 7 in solution. That's kind of where they get their name from. So if you put these into a solution of water, the pH would be more on the basic end, which is alkaline. So that's why you get alkaline earth metals. These metals are not found just by themselves in nature. You're not just going to stumble upon calcium by itself or magnesium by itself. You're always going to find it bonded with something else. So there's some processing involved to get any of these metals in by themselves. Through the middle part here, we have the transition metals. So this is groups 3 through 12. Just some things we know about them. The physical characteristics would be that they're shiny. Some of them will be malleable, more malleable than others, but in general, metals are shiny. You can change their shape. So they do have valence electrons, just like anything else, but their valence electrons can be present in more than one shell. So like the outer 2 shells can be unstable, meaning that they can share electrons from both their outermost shells, which no other groups of atoms can do that. So when we start talking about bonding, we'll start talking about metallic bonding, and it's called like a sea of electrons. So they bond kind of in a different way. But for now, what we need to know about these is just this information. So it's this middle section of your periodic table. They can have more than one valence shell, basically, and they can bond in different ways because of that. Down at the bottom, you have your rare earth metals. Okay, so group, like this is like your F sublevel down here. The first family is going to be the lanthanide series. This is group 3, period 6. These are found in nature, so you could, find cerium or erbium or whichever, lucium. There's a whole bunch of down here. You could find these on Earth somewhere. They have been discovered. And then down beneath that, you can have the actinide series. All of these are radioactive, and they're mostly just man-made. So we know that radioactive means that they're not stable. Somewhere along the line, the neutrons have been altered. So most of these are man-made. They've forced these atoms to exist. They wouldn't just exist in nature in any situation. Other things on the periodic table. So some of these are metals, some of these are non-metals. That's kind of a bad, I need to fix that. So you have your boron family, carbon family, nitrogen family, oxygen, halogen, and noble gases. These correlate with the first atom in the top of that row. So you'll find that boron is at the top here, carbon, nitrogen, oxygen. And then fluorine would be the beginning for your halogens, and then your noble gas family. So we already know this about the valence electrons. Okay, so you start with 3 valence electrons and work your way over. If you look on your periodic tables, you would see kind of there's like a stair step that goes down here. So within these families, you do have a mix between like semi-metals or like metals and non-metals a little bit there. So then you get over here to the halogens. This is group 17. So you're on the opposite side of the periodic table here. These all have 7 valence electrons. Okay, so in the same way that the alkali and alkaline metals were very reactive because they want to get rid of an electron, these are very reactive because they want to gain one electron to become stable. They're going to have a very strong pull, a very strong attraction for electrons. And it'll be easy for them to bond. So again, very reactive, the halogens are. So for these, it's opposite of the other side of your periodic table. So over here on the alkali metals, as you move down, these become more reactive. On this side, as you move up, they become more reactive. So up here at the top, you have fluorine. Fluorine's going to be your most reactive non-metal. So this is part of your halogen group. So is going to decrease as you go down. So these are your halides. These form salts. Okay, so these are going to bond with your alkali metals very easily because these have one electron to give and these need one electron to gain. So they're going to bond with the alkali metals very readily and form different salts. Your last group here is going to be your noble gases. Group 18, helium is included up here because of its stability. We know that this one only has 2 valence shell electrons, but it only has 2 at all. So that makes it stable. That first ring only can hold 2. So it has 2 electrons. It's stable. All of these noble gases, all the rest of them have 8 valence shell electrons. They are not reactive or have a very, very low reactivity. They can react in certain situations, but it's very rare. Helium, neon, and argon do not react, and then you do have xenon, krypton, and radon that do react in certain situations, but not very often. So they're not really going to react because they don't need to. They don't need to gain or lose electrons to become stable. So they're not interested. They just don't need it. They don't need any more electrons, and they're certainly not going to give up electrons to become unstable. So the last thing we're going to talk about, I told you this one's long today. Last one we talk about is electron configuration and the periodic properties. So we've talked about the actual arrangement of electrons for electron configuration, but this is how that all relates to your periodic properties. So again, if you want to pause this, check out your success indicators to know how you know if you're being successful in this section. So we're just going to run through these. If you have a periodic table printed out, it might be useful to draw these on here as we go. This is also part of the assignment today, so if you want to pull that up and maybe have it on another screen or like a dual screen here. So it's just some trends as we go across the periodic table. We know that they're already organized by atomic number, and they're naturally fall into these groups with similar characteristics. So there's some other trends that go along with that as well. Electron and affinity. Okay, so electron affinity is the amount of energy released when an electron is added. So electron affinity increases as you move from left to right and from bottom to top. So electron affinity is very high in the top right corner of the periodic table. So like all of these over here would have a high electron affinity, meaning that they're releasing a lot of energy whenever they're bonding with something, and then that would decrease towards this end of the periodic table. Electronegativity would be the next one. We'll talk about electronegativity kind of frequently. So electronegativity is the measurement of the attraction of an atom for a pair of shared electrons it shares with another atom. Okay, so if you look at these, the size of these dots is representing the amount of electronegativity they have. So the higher or the larger these dots are, the higher the electronegativity, the more likely they are to share electrons with another atom. Atomic radius is going to be just your actual like physical size of an atom, of a neutral atom. Okay, so we know that the electrons are surrounding the nucleus in a cloud type arrangement, and there's a radius that can be measured of that. So the atomic radius is going to be the measurement of from the nucleus out to the edge of that electron cloud. And it gets larger as you move to the bottom left-hand side of the periodic table, and smaller as you move to the top right-hand side of the periodic table. Part of the reason for that is that, like I said, these only have one valence shell electron, so they're trying to get rid of that. The nucleus is not holding on to those electrons very strongly, so the bond between, not really a bond, but the attraction between the nucleus and its electrons is weaker for these down in this area than it is up here. These, like we talked about a minute ago with the halogens, the fluorine has 7 valence shell electrons. It's not going to give them up. It wants to gain one. So it's going to be very attracted to its electrons. It does not want to lose them. So that's kind of what this atomic radius is showing. So if it has a very large atomic radius, those electrons are not very strongly attracted to the nucleus. Ionic radius, we won't talk about this one a whole lot, but it's the same sort of idea. So if we have an ion of something, we know that an ion means that it has gained or lost electrons. That's obviously going to change the atomic, the radius, right? So if fluorine looks like this one here, the smaller radius, and then you add an electron to it, that's going to change its radius because you're altering how many electrons are in its electron cloud. So same kind of trend here. So it's going to become a larger ionic radius towards the bottom left and smaller towards the top right. Ionization energy, we're almost done here. So ionization energy is a measurement of the energy required to take away an electron from a neutral atom. So in other words, it's like the likelihood of an atom to lose an electron. So if you have a high ionization energy, it's going to require a lot of energy to remove an electron from that atom. And so down here, this little menu popped up again. I'll stop moving my mouse. In the bottom left-hand corner, you're going to have low ionization energy. So again, this all kind of goes back to your valence electrons and how those are arranged. So in that bottom left-hand corner, you get like cesium and francium, barium, all those down in that corner. It's not going to take a lot of energy to remove one of their electrons. They're trying to get rid of that electron so that they can become more stable. And then in the top right-hand corner, again, like you have all of your noble gases, those aren't going to bond with anything. So they have a very high ionization energy. The halogens, the oxygen family, all of those have a very high ionization energy because they're trying to keep their electrons because they want to stay or become more stable. And then I think this is the last one here, just talking about the metal versus non-metal reactivity. So these are the tendencies of these atoms to react with something else. So again, kind of follows that same pattern as everything else has. They're going to be more reactive on the left-hand side of the periodic table because they have fewer valence electrons. They're going to be more reactive towards the bottom of the periodic table because those atomic radii are larger, so the nucleus has less of an attraction to its electrons. So you're going to be more reactive towards the bottom and then more reactive towards the left. So even so, just in general, everything on the left-hand side will be fairly reactive, and everything on the right-hand side will be much less reactive as far as getting rid of their electrons. So this is the very last slide, just kind of puts it all together. It shows all of these trends together. You also have like your melting and boiling points in here. Melting points or boiling points will be highest towards the center, which makes sense because these are your transition metals. So these are going to be harder to add energy and force it to rearrange. So that's like another one you'd want to add on there. But these trends will be important when we start talking about bonding. So if we have a high electronegativity, it's going to be more likely to accept an electron than to give up an electron. So that's going to kind of shape us when we start talking about bonding on whether it be a covalent bond versus an ionic bond, or if it's polar, non-polar, and we'll talk about all that. But these are kind of like a building block for us as we move forward. So it's important to get familiar with these, understand what they are, and then when we use this in the future, you'll know what we're talking about. And that's it. So please go back, check out those videos, and watch those. Those are pretty neat. And then check out the assignment on Canvas. We are playing a game in class, and I'm going to just excuse you guys from that because it would be very difficult to figure out how to do that because it's like a card game. But it's just going over these trends. So maybe if you need a little extra help on these trends, let me know, but your assignment should give you plenty of practice on this. So get that assignment done. Let me know if you have any questions, and I will talk to you guys next time.